Good morning, everyone. We're going to pick back up in chapter 9 this morning. Hope you enjoyed the walk in. Anybody put Christmas music on in their earbuds today? Winter Wonderland? I don't know. It's really pretty outside. I hit one patch of icy road driving in here today, and there was a car like forever in front of me, and I'm on this ever so slight downhill, this downgrade, and brakes just nothing. And so I'm like, that car better get out of my way. And it was funny that was the only stretch of icy road in my whole drive in. And it's like the only stretch I actually kind of almost needed to stop on. So if you're driving today, careful. But anyways, we were on this slide last time. We're trying to discuss the bond angle trend here, where for methane, the bond angle is perfectly 109.5 degrees the whole way around. And if we wanted to go to like geometry class, we could prove or show that for a tetrahedron, that all the bond angles precisely are exactly 109.5 degrees. So we won't go through the derivation of this particular measure, but when it's perfect tetrahedral, all the bond angles are exactly the same the whole way around the molecule. And so whenever we look at a bond angle like in ammonia and see that the bond angle here is actually closer to 107, not 109, we can try to make sense of why that's the case. Now, the case for ammonia is that this lone pair of electrons, they're actually going to be closer to the nitrogen atom. So if we're thinking of the ammonia molecule, think of how these two electrons here are going to be closer to the nitrogen atom. And of course, those electrons are negatively charged, and so they have a negative charge. And those electrons are going to repel the bonding pair negative electrons, and it's going to push those atoms to be closer together due to the negative electron repulsion. So the issue is our non-bonding pair of electrons, that the electrons are going to be closer to the nucleus and therefore just exert a greater repulsion on the bonding pair. A bond pair is going to stretch the two electrons out to be further away from each other. So two bonding pair electrons, they don't repel each other as much as the bond pair are repelled by the lone pair. So our lone pair repulsions are greater than the bond pair repulsions, or what we can conclude from the bond angles of ammonia. And then if you consider having two lone pairs, like on water, where we have two lone pairs. Now, for the geometry of water, for some reason, we ignore the electron pairs in terms of the name of the shape. For water, if you remember, we call the molecular geometry just where the atoms are to be bent. The name for ammonia is trigonal pyramidal. It's just a pyramid that has a triangle base, is what the ammonia name is referring to. But these lone pairs are going to be closer to the O atom, therefore pressing the bonds to be closer together. So it's even less than ammonia's bond, so close to about 104.5. Now, I wouldn't expect that you memorize these bond angles. I would just expect that we imagine that anytime we have an atom with two lone pairs and then therefore a bent bond, so like this here, that I would just expect us to know that this bond angle should be less than 109.5 degrees. If it were perfect tetrahedral, it would have been exactly 109.5, but anytime we have two lone pairs, they're going to repel each other more. The bond pairs don't repel each other as much, so those bonds are going to get closer together than they would within the perfect tetrahedral geometry. And we'll see this within some other geometries too, that we'll kind of get a glimpse of, well, what does the perfect bond angle look like within a given geometry, and then how might a lone pair disrupt that perfect kind of nature of those bond angles we might have expected. So let's press forward into a kind of glimpse at having 2 verse 3 verse 4 total domains. And so whenever we have two total domains that are bonding domains, now if we think about a molecule, we have to have at least 3 atoms to talk about a geometry. If we're at a diatomic molecule, if we just have like N2O2 CO, I mean, we know that that's just a linear connection of the two atoms. Once we have a third atom, then the question becomes, when we have 3 atoms connected, are those bonds just connected with bonding domains with no lone pairs? So like the lowest number of domains we can have is 2, and they both have to be bonding. If we had 2 total domains, one was non-bonding, that's just like some kind of diatomic molecule. So our least number of bonding domains we can have in total domains is 2. None of them can be non-bonding domains, meaning there's no lone pairs on the central atom. So if we're thinking of their lone pairs, there's no lone pairs on the central atom. A good example of this is CO2. So CO2 exists with a linear bond, and this bond angle has to be exactly 180 degrees because it's perfectly linear. So whenever a bond is linear, it should be exactly 180 degrees. And so anytime we have 2 total domains, it would fit into this geometry. So another example would be a molecule like HCN, where we have a triple bond, no lone pairs on carbon, so this bond angle here has to also be a perfect 180 degrees. So anytime we have two total domains, now a double bond or a triple bond, the number of bonds between an atom and a partner is just counted as one domain. So these count as, domain number 1, domain number 2, so this is two total domains. And they're both bonding, so they're both bonding domains, just like CO2. I don't look at the double bond and say that the double bond is two domains. A double bond is just one domain, the other double bond is the other domain. So one domain here, the other domain there. Because those are the two domains that repel each other and force the structure into that 180-degree geometry. Now think about CO2. It doesn't want to be bent because it's going to put those domains too close together, they're going to repel. So the domains are trying to get as far away from each other as possible. When we have three total domains, the basic structure is going to take the trigonal planar geometry. And the trigonal planar geometry is just, well, we have three domains. How can they get as far away from each other as possible? If we kept it at linear for this in the central atoms here, and we try to put a lone pair, that lone pair is interacting with the bond pairs at 90-degree angles. That's not good. So we don't want to just take our linear geometry and stick a lone pair. The bond's going to have to bend. The lone pair is going to have to take a spot if we have a lone pair. But we're going to fit into the basic geometry of trigonal planar. So trigonal planar is what we call the electron domain geometry anytime we have three total domains. So this is what we call the electron domain geometry whenever we have three total domains. Now we can get to three total domains two different ways, either from all of them being bonding domains. An example, that's BF3. So if we're looking at our Lewis structure of BF3, we remember that it has three bonds to fluorine, no lone pairs on boron. If we remember, we tried to stress a lot with the Lewis structure. We don't have electrons left over to put a lone pair on boron. So then we have three total domains, no lone pair on boron. So this structure here is going to take the trigonal planar electron domain geometry. Then we also call that its molecular geometry. So its molecular geometry name is trigonal planar as well. So you kind of have two different domains. Now, when all the domains are bonding, the names are the same. But when you have a non-bonding domain, so another possibility for three totals, when we have two bonding plus one non-bonding, of course, that's three total. And so if you just imagine having a pair of electrons in one of the spots of our trigonal planar geometry, then that's going to kick into the bent molecular geometry. The name bent is going to come from maybe a molecule like NO2 minus, where we have a lone pair on nitrogen. So three total domains, so domain number 1, domain number 2, domain number 3. And so we have three total domains, two of them are bonding, one's a non-bonding domain. And so then we're just looking at the atoms now and trying to say, well, what's the name of the shape of the atoms? Certainly not linear. So whenever we have three atoms, if you go back to a slide from Friday, three total atoms, the question is it perfectly linear or is it some kind of bent structure? This structure here would have to be bent. So we call it a bent molecular geometry. Now, what do we expect this bond angle to be? Well, we'd expect it to be 120 degrees if it were perfectly within the trigonal planar geometry. Like BF3's angles are all perfectly 120 the whole way around. There's no reason why they wouldn't be. But now we can predict that the bond angles in NO2 minus should be a little less than 120 because we get that extra lone pair repulsion pushing the O's a little bit closer together. Now, how much less than 120? I wouldn't worry too much about it, but it's probably like 117-ish, something like how, ammonia was like 2.5 degrees less than kind of perfect tetrahedral. So this is probably a couple degrees shy of 120 degrees. One other thing to mention for NO2 minus is you could have been a little confused and thought, well, what about resonance where we have this resonance effect over to here? Well, resonance doesn't change the total number of domains. So when I look at a different resonance structure and kind of say for NO2 minus, both those bonds, one's not really double, the other's really not single. They're both kind of in that weird three halves compositing effect, that doesn't change the molecular geometry name, that we still have three total domains. So if we're picturing either one of these two Lewis structures, we still have three domains. Or if I'm picturing the composite average structure, which looks something like this, that I still have three total domains. So if you were thinking, does resonance play any kind of role in the geometry name? Not really. It's not that we can necessarily ignore resonance. It's still going to take place. We may still want to think about its importance for understanding an ion like this particular one here, but it's not going to change the name. No matter which of the resonance structures, if you call resonance structure A versus resonance structure B versus the compositing, which call this one maybe the true, because this is a better picture of what the true ion looks like as the average of A and B, and it never really ever being A or B, and it not being a fast equilibrium. Resonance is kind of like an all-time effect where that electron pair is going to distribute across the two bonds at all times, but it doesn't change the fact that we still have two total bonding domains, one non-bonding domain. Now, if you then said, well, what about one bonding domain, two non-bonding domains? Do you see how if we reduce this bonding domain to 1 plus 2 non-bonding, that just goes back to a diatomic molecule? Like if I only have one bonding pair between an atom and some other partner, then that's just a diatomic molecule. The geometry of a diatomic molecule is just a straight, atom-to-atom connection. So we're not really concerning ourselves with diatomic molecules. So once we get past two bonding domains for this geometry, we wouldn't have, a 3+ atom molecule anymore. Okay, so let's look at tetrahedral. So for tetrahedral, we have three possibilities that we saw before. We've already seen these, so maybe we'll go quickly through these. But we saw tetrahedral CH4, so perfect 109.5 degrees all the way around. We saw ammonia with its lone pair being trigonal pyramidal, approximately 107. But let's just say here, I'd expect that you would just know it's less than 109.5 degree bond angles, and water, two lone pairs in the bent geometry, so certainly not linear, and this would be less than 109.5 degrees. If we're rank ordering, we'd probably expect it to be less than something with only one lone pair. So having two lone pairs probably presses the bond angle more than just having one lone pair. So you'll see a couple questions on some practice quizzes, maybe some lecture examples later that kind of compare relative bond angle trends, where you're generally trying to see, well, what structures are like CH4 that have to be perfectly 109.5, what structures are going to be a little less than the predicted angles using the lone pair, bond pair repulsion kind of model. Okay, so that's for having four total domains, so either 3 bonding plus 1 non-bonding or 2 bonding plus 2 non-bonding. So, and then once we were to get to 1 bond plus 3 non-bonds, that goes back to diatomic. So we have to at least have 2 bonding domains to have an actual geometry to consider. Okay, so we'll move on from here. Let's move on to then the larger domains. So let's take a look at what it looks like to have 5 or 6 total domains. And let's even then just kind of go back to the quick summary of the AB2 linear, 180, trigonal planar, tetrahedral. But the other two structures that we have for 5 and 6 total domains fits into a geometry that we call trigonal bipyramidal. Now, where does this name come from? Well, we get a trigonal plane in the middle. So if you look in the middle, it looks just like BF3 did, where it had 120 degree bond angles around, sometimes we call this the equator. So we call this sometimes the equator of the molecule, like maybe the equatorial positions too, you'll hear us say. If you notice, the equator has 3 atoms in 120 degrees, so we'd have one here, one sticking straight behind us. Another way of sketching this could be if we had to write this, I'm picturing a central atom, let's call it A, and then I maybe have a B that's in the plane, and then I'm picturing a B going back and a B coming straight at us, where all of these angles are perfectly 120. And then above and below, I have my other connections to my other atoms. And then those are on an axis relative to each other. So we call those the axial positions. So our axial position atoms, if you notice, they're on an axis together. And then the equatorial positions, they're on the equator relative to each other. So we have 2 different base bond angles within the trigonal bipyramidal geometry. On the equator, we have 120 degree bond angles, and then the bond angles for the axial to the equatorials, those are at 90 degrees, and then of course the axial to themselves, that would be 180. So we have that 180 degree bond angle as well within the structure. So we have a couple of different bond angles within the trigonal bipyramidal geometry, but that's how molecules have sorted out the problem of having 5 total domains and spreading those domains out geometrically. We'll look at a couple examples in a minute of molecules that fall into that geometry, but another geometry that we see, and this will be the highest that we go, we don't go past 6 total domains or 6 total bonding pairs on a central atom, but that would be like an AB6 structure. And if you notice, the name's kind of peculiar. It's like octahedral, and you might have expected to be hexahedral. Since there's 6 bonding pairs, why would we go with a name that suggests that there's 8 of something, even though it appears there's only 6 of something? Well, it goes back to kind of the idea that tetrahedral was tetrahedral because of the number of faces we got. Remember how I mentioned the tetrahedron is the structure that's made about by the outer like atoms connected together. I get a 4-sided pyramid. So if we picture this pyramid here, that's how we get like a 4-sided shape. And it happens to have 4 atoms that cause it. So tetrahedral is interesting. It has 4 atoms, cause there to be 4 shapes or 4-sided pyramid. But now with my octahedral, because I have this one position up, then I have 4 atoms that look like they're on the equator. So there's like 4 atoms outside of 3 along the equator of the molecule. That gives me a 4-sided pyramid on the top. So I get a 1, 2, 3, 4-sided pyramid on the top, and the same thing on the bottom. So I get a 4-sided pyramid on the bottom. So the pyramid shape, if you connect the atoms, you get a 4-sided pyramid on top and a 4-sided pyramid on the bottom. So that's why we call that structure an octahedron. So it fits into like this base structure here. So you can see 4 shapes here and then 4 sides to the shape below. So 8 total sides to the pyramid shape that you're getting. Now this leads to a few things. Like we could have called trigonal bipyramidal. I guess we could have called that hexahedral, but I think that would have been confusing to call, because it looks like there's 3 pyramids on the top, 3 on the bottom. So I think we could have called the AB5 trigonal bipyramidal hexahedral, but I think that would kind of have been a confusing name. We could have also called octahedral square bipyramidal. In fact, I kind of wish we did, because that fits in with trigonal bipyramidal really well. So another name you could think here that would be pretty appropriate would be square, because we get that square kind of like plane around the equator, and then bipyramidal. So just a bipyramidal just means you get 2 pyramids, a pyramid on the top and a pyramid on the bottom. So instead of trigonal bipyramidal, it'll just be square bipyramidal. Now that name might make sense a little bit later on why we might have suggested square bipyramidal as an alternative to octahedral. Let's show the structure down here. So here's the octahedral structure drawn like a second time, where we see 90-degree bond angles throughout the structure. So in octahedral, we don't have this issue with there being 2 different types of bonds. All of the connections of 2 atoms are on an axis together. So we have 3 axes of atoms. So if we're trying to sketch an octahedral, if I have a central atom, let's keep it consistent and call it A. So if I have a central atom A, and I'm trying to draw the octahedral geometry, I draw like a structure on top and bottom, and I have 2 kind of choices. And this is the way I usually like to do it, because I think it's a little bit easier to sketch. I then sketch another set of atoms. Whenever I'm not like dashing arrows, that's in the plane of the page that I'm writing on. And I can certainly picture having sort of a square plane of atoms like this here, and then I can picture here a B going straight back and then a B coming straight out of the page. Now this is a little bit hard to sketch, because literally what I'm trying to think is, like if I take my like Apple Pencil or whatever on the screen, like imagine straight out of the A atom, sticking straight up is the B atom and going into the page in the same way. So we're trying to wedge like right into the page, right sticking out of the page, that B atom. So another way I can sketch this, because sometimes it's, if we can't sketch these shapes, it's going to be hard for us to picture them. If you can sketch the shape, I think you can probably picture the idea. Another way we can sketch this is to have A, B on top, B on bottom, and then imagine wedging a B this way, and a B this way, and a B this way, and a B that way. And so these atoms are on an axis together, these atoms are on an axis together, and they're just sticking kind of straight out of the page, but wedging out. And so all these bond angles are 90 degrees across the structure. I won't write all of them in, but every structure here is perfectly 90 degrees within octahedral geometry. And so the only structure that has 2 different types of bonds in 2 different environments is trigonal bipyramidal. Every other structure, every position is more or less identical. So like on tetrahedral, When I'm writing ammonia and I need to choose, where do I want to put the lone pair? Do I put the lone pair, this position? Do I put the lone pair on that position? Does it matter? The answer is it doesn't really matter. It's kind of easier to choose the top position, I think, just for sketching purposes. So like if you're trying to sketch the structure, there might be a way that's easier than others to actually show what the geometry looks like, but it doesn't practically matter. I could put the lone pair anywhere, the bonding domains anywhere, but now trigonal bipyramidal, I'm gonna have a choice. It's gonna be different if I choose to put an electron pair on the axial versus the equatorial position. So we're gonna have to think a little bit about trigonal bipyramidal. Okay, so then let's look at the geometries we get for having 5 total domains. So if I have 5 total domains, one example of a molecule that has all bonding domains is something like PF5 or PCl5. So a structure like PCl5 or PF5, this just has a central phosphorus that has 5 bonding pairs to chlorine, where chlorine has electron pairs all the way around. And then we have no extra lone pairs on phosphorus. So we end up with 5 total bonding domains. The count of electrons for something like PCl5 would just be 5 for phosphorus, that's its valence count, 5 times 7 for the chlorines, that's 40 total electrons. So that's 8 per chlorine. So no lone pairs. I just want to make sure that we see that we have phosphorus with 5 bonds to chlorine, 0 lone pair electrons in its Lewis structure. And then the way it's going to arrange those bonds is within that trigonal bipyramidal geometry. And so it has the same molecular geometry and electron domain geometry name, takes on the structure that we were talking about for trigonal bipyramidal. Now, a molecule that has a lone pair on the central atom then also has 4 bonding domains. So if I have 4 plus 1, that's of course 5 total. It would fit into this electron domain geometry. Remember, anytime you sum up to the total number of domains to be 4, it's tetrahedral. If it's 5, it's trigonal bipyramidal. We call that electron domain geometry. But then what we want to try to think is, well, what's the shape of the atoms? And then the real question is, do I put the lone pairs here or do I put them here? Because I have a choice. And this is the only structure where there's a difference. I get a different structure if I put the electron pairs on the top structure in the axial position versus on the equator. Well, it turns out that the way you figure this out is you look at nature. You look at the real molecule and you try to say, well, what's the structure of the real molecule? What does it really look like? It really looks like this seesaw structure here, where I have a lone pair on the equator of the atom. Now, the position of the equator you put the lone pair doesn't matter. I could put the lone pair here, or I could put the lone pair here or here. I get the same geometry. I just don't get the same geometry if I choose the axial position. So I can choose any of the equatorial positions to put the lone pair on. Then I connect my fluorines to the molecule, and then I have my 5 total domains. If you're counting electrons, just making sure you see the Lewis structure, you would have 6 plus 4 times 7, that's 34 electrons. So 8 around each fluorine, that's 32 electrons. The 2 electrons left over go on to the central atom. So that's how we would know. If we just said SF4, what's its Lewis structure? Hopefully we go back to chapter 8 and we're seeing that sulfur should have 2 lone pairs on the central atom. And so then the structure that SF4 takes is it's going to take, again, it's going to take the equatorial position instead of the axial position. So it's going to take a lone pair on the equator of the atom and then kick the structure into what we would call, and then that becomes a question, well, what's geometry name do you call this structure? Well, do you see that this structure would like teeter-totter on itself? It's a really weird way to give it its name, but they call this the seesaw molecular geometry. It looks like a teeter-totter. It looks like a thing you would sit on when you're a kid and go up and down. And so that's the name of the shape. So we're trying to say, well, what shape do you give this name here? If you're not seeing it, and I think probably it's not too hard to see, but just picture the structure this way with the lone pairs coming out here, or not the lone pairs, the atoms coming out here, lone pair residing on the other equatorial position. So I think you can see that looks like a teeter-totter or a seesaw. So that's why we call that the seesaw molecular geometry of SF4. And then the electron pairs are going on to the equator. And then you can even see the bond angles aren't perfect 120, 180 anymore. The bond angle from the electron pair is going to press these atoms closer together. They give the geometry kind of in a weird way. They're saying that the atoms from the one side to the other is 186. I think it makes more sense to talk about this bond angle here, which would be 174 degrees. you can call the bond angle either the 174 or you can call the bond angle the opposite, but it's showing you it's 186 if you take the bond angle from the bond being compressed. I like to almost think, well, it's less than 180 for the actual bond angle. Instead of it being perfect, it's being compressed. So that should be 174. For some reason, the picture, they're giving you the bond angle 186 the other way around the atoms. Hopefully that makes sense. But this bond angle is definitely less than 180 degrees because of the bond pair interactions being less than that lone pair interactions with the bond pairs. And this should have been 120. So this bond angle here is less than 120 due to the compression with the lone pair. So anytime you have a lone pair, you're going to distort a little bit off the bond angles that you expect off of the perfect angles within the base geometry. Now what about CLF3? So CLF3, let me zoom in a little bit. So CLF3 would have 2 lone pairs on chlorine. How do we know this? Well, just think of the Lewis structure for having 3 fluorines attached to a central chlorine. Put lone pairs around the fluorines. Let's count our electrons. There's 7 for each of the atom there, so that's 28 total valence electrons. I've assigned 8 times 3 around the fluorines, that's 24. The 4 electrons left over, lone pairs onto chlorine. And so then the best structure, and it maintains using the equator. Now, this is something I think we just have to more or less memorize, that the equatorial positions are where we're going to put the lone pairs. Now, why the equatorial positions? What you can imagine is the molecule is kind of choosing to put the electron pairs wherever just is least interactive, where you have the least repulsions total across the whole molecule. And so nature is kind of dictating, well, this must be the best geometry. And it takes a shape that kind of looks, if you invert it, like a T. So if you look at this structure here, that looks like a capital T structure. So we call it the T-shaped molecular geometry. We get that anytime you have 3 total bonding domains, 2 non-bonding domains. So you can't get to this geometry any other way. So the only way you can get a molecule into this particular molecular geometry is to have 3 total bonding domains and 2 non-bonding domains to kick it into this geometry. If you remember, we only had 1 pair of electrons with the 3 domains. That's like ammonia. That's trigonal bipyramidal. So the second domain kicks it into this T shape. Now, do we expect these bond angles to be perfectly 90 degrees here? No, probably less than 90. So the bond angle here should be a little less than 90 degrees because of the lone pairs pressing the bonding pair electrons closer together. There's not a lot of examples of molecules that do the next geometry, but the next geometry is having 2 total domains, 2 total bonding domains, 3 non-bonding domains. Of course, that's 5 total. So we would say SF4, CLF3, and now xenon F2 all share the electron domain geometry of trigonal bipyramidal. So the electron domain geometries are all trigonal bipyramidal for these structures, but the name of the shape of the atoms, the molecular geometry names are different. So SF4, seesaw, CLF3, T-shape. Now xenon F2 continues the trend of putting the electron pairs on the equator of the atom and then leaving the fluorines on the equator. How do I know I get this structure? Well, xenon, well, one, you may be confused at first because xenon's a noble gas. A noble gas that's big, like xenon, will eventually react with something like fluorine under very peculiar conditions, usually at very low temperatures. This isn't a stable compound that you can put into like a bottle and ship and buy from a chemical company, but this is something you can make at low temperatures and study before it can decompose. But then you would have 2 times 7 for the fluorine, so 8 valence electrons for xenon plus 2 times 7 gives us a total of 22 valence electrons. And so in terms of a Lewis structure, that's a central xenon, 2 fluorines, lone pairs around them. That's 16 electrons. So I have 6 electrons left over. That's the electrons on xenon. And so that's how you can see. If you're wondering, how do I know for sure you get those 3 non-bonds around xenon? It's just by sketching a Lewis structure and seeing that we end up with 1, 2, 3 non-bonding domains plus the 2 bonding domains. And so the bonds go on the axis of the atom. Now, this is a interesting question. What do you think this bond angle is? Do you think it's perfectly 180? It's actually perfectly 180. because it has electron pairs pressing on it from every direction. So one lone pair, if it tries to push the fluorines together, the other lone pairs pushes it right back. So the bond angle maintains at a perfect 180 within this structure. Okay, now the last examples then go to the case of octahedral. So octahedral, if we have 6 domains, that's an easy, they're all bonding, like SF6. SF6 has, essential sulfur, 6 fluorines. Each fluorine has 3 lone pairs around it. Just making sure we see the Lewis structure and make sense of it. So I have 6 for sulfur, 6 times 7 for the fluorines. That's 48 total. If you notice, that's a multiple of 8. So I have 8 electrons around each of the fluorines. There's 6 of them, so that's all 48 electrons, none left over for sulfur. Just making sure that we have 6 fluorines attached to sulfur with no lone pairs on sulfur. And we can easily get to that Lewis structure. And so no electrons left over for sulfur within this Lewis structure. So if all of the bonds or if all the domains are bonding domains, then the molecular geometry name is octahedral, just like the electron domain geometry. And so again, just remember that this geometry here, this is our electron domain geometry name. That's the electron domain name for all the geometries that share that domain count. And so what if we have 1 non-bonding domain, 5 bonding domains? IF5 is an example that does this. So IF5 would have, iodine has 7 valence electrons. They all have 7. So IF5 or BRF5, either one of them. The example in the picture here is BRF5, but all halogens have 7 valence electrons, so that's just 7 times 6 total. That's 42 valence electrons. Notice that's 2 over a multiple of 8. So I have 8 electrons around each of the fluorines. There's 5 fluorines, so that's 40 of the electrons. Just making sure we see where those 2 electrons come from in our valence count. We get those 2 extra electrons that go onto the central atom of iodine. A quick sidetrack would be, what's the formal charge of iodine in this Lewis structure? Do you guys think it's 0 or something other than 0? Well, the formal charge of iodine, remember, it should have 7 to be neutral, and it has, let me get a laser pointer, it has 1, 2, 3, 4, 5, 6, 7 around it, so it's perfectly neutral. So all these atoms happen to be 0 formal charged. Just to kind of go back to a quick formal charge check, if you go to SF6, they're all 0. A lot of the structures in this example, all the atoms have 0 formal charges if you were to go back and double check those formal charges. But anyways, we have the extra lone pair on iodine. So it doesn't matter what position you choose. You can choose any of the 6 positions, you get the same shape. You get the same shape to emerge for octahedral because all these positions are the same as each other. So I can choose here, or I can choose here, or here, and I get the same structure. So there's no difference between axial versus equatorial on the octahedral structure. All the bond angles are 90 degrees across the whole structure, so I can choose any particular structure. So we choose the bottom within the structure here. Now, do you see the name you might give that? Like when we went to the square bipyramidal for octahedral, I've lost the pyramid. So what if I just call this geometry name square pyramidal? So if you notice, it's not bipyramidal because I only get 1 pyramid. So trigonal pyramidal back to ammonia has 1 pyramid, so it's just a pyramidal structure. The trigonal bipyramidal is a bipyramid because there's 2 pyramids. There's the top and the bottom pyramid. Here I just get the one-sided pyramid. So I only have 1 pyramid with 4 sides on top, so hence square pyramidal. You can memorize the names and the shapes and put it on flashcards, that's fine, but if you can picture the shapes and see them and understand that the name comes from something that we can see and put a picture to, you can really make sense of the names and understand them. If we then go to a structure like xenon F4, so xenon will form a bond with 4 fluorines. The valence count to see how you get xenon with 2 lone pairs is 8 for xenon, 4 times 7 for the chlorines, that's 28 plus 8. That's 36 total electrons. And so for xenon F4, in terms of a Lewis structure, where do I want to put this? Let's put this over here. So for xenon F4, I put my 4 fluorines. Each of them have their lone pairs. So that's 32 electrons. So that leaves 4 electrons behind for xenon to have 2 pairs. So those last electrons go on to xenon. So xenon now is going to have 4 total bonding domains. And so 4 bonding domains, 1, 2, 3, 4, and then plus 2 non-bonding domains. And so obviously that's 6 total. So 6 total domains fits into octahedral electron domain geometry. And then we're going to choose the electrons to be on the axis relative to each other. So whichever electron pair we kind of replaced for like our square bipyramidal, we'll just put the electron pairs on the same axes. We don't want the electron pairs to be 90 degrees relative to each other. They repel each other. They want to be as far away from each other as they can get in the structure. And so xenon F4 takes a structure of square planar. So a planar structure means all the atoms are in one plane. So anytime we call a structure something planar, it means all the atoms are in one single plane. So all 5 of these atoms are in the same plane as each other. So they're all in that square plane center of the molecule. You can call that the equator of the molecule if that helps. But just remember for octahedral, the equator positions are the same as the axial. There's no difference for the equatorial versus axial like there was for trigonal bipyramidal. Now, we could continue to 3 plus 3 and 2 plus 3, but we don't see examples that are common for those. So this is like the last structure that we go over, and would expect you that if you see a structure that has 4 total bonding domains, 2 non-bonding, we would expect that you would know it should be a square planar molecular geometry within the octahedral electron domain. There's not a lot of examples of these more exotic structures. Like there's not a lot of things that look like BRF5 and IF5. There's not a lot of examples. The key is really just making sure you can sketch a Lewis structure and get the correct number of bonds and the correct number of non-bonding pairs on a central atom. If you can do that, it should be pretty easy to kind of try to picture the shape. If it's 2 total domains, it's like CO2. If it's 3 total domains, it's like BF3. If it's like 4 total, it's like CH4. If it's 5 total, it's like PF5 or PCl5, trigonal bipyramidal. If it's 6 total, it's like SF6. Okay. Now let's look bond angles real quick. So these bond angles perfectly 90 degrees for the square planar. They have electron pairs pressing on either side, so those are exactly 90 degrees. And then the square planar angles would be a little less than 90 degrees. So these bond angles here should be a little bit less than 90 degrees due to that lone pair pushing the atoms to be a little bit closer together. Now, the one reason why I like to stress bond angles is for our next topic of polarity. When I start thinking of bond polarity, if I can think of structures that kind of have a peculiarness about their bond angle changing due to lone pair repulsions, that might be one way for me to see and predict if the molecule should be nonpolar. Before we get there, I forgot the slide first. Let's look at a couple bond angle predictions for a few other molecules. Double bonds will actually repel a single bond to a greater extent because we have 4 electrons. So I have 4 electrons here. I only have 2 electrons here. So the 4 electron bond's going to press the 2 electron bonds to be a little bit closer together. So my bond angle for the chlorine to chlorine, this bond angle here should have been about 120 degrees because this should be trigonal planar geometry, but ends up being a little bit less than 120. And then this bond angle here, which should have been 120, we can predict it to be a little bit greater than 120. And so we can see these bond angles here in the real structure, about 124. And that's just because a double bond will repel a single bond to a greater extent than 2 single bonds will repel each other. So we have a similar type situation, like lone pairs can repel each bonding pair electrons to a greater extent. Here, a double bond repels the single bonds to a greater extent. So the 2 single bond angles get a little bit closer together, but still, both of these structures are still planar. So these are still within the trigonal planar domain, because we still have 3 total domains. So we're not kicking the bonding pairs out of the plane. They're still staying in the plane. It's just a question of, do these 2 chlorines get a little bit closer together? So the chlorines just get a little bit closer together than they would otherwise due to that extra repulsion with the lone pair. Now let's compare a couple of different Lewis structures. Let's look at SO3 for a minute. So let's predict bond angles. To do that, let's look at a Lewis structure for SO3. So it'd be 6 plus 3 times 6. That's a total of 24 valence electrons. Now when I get to SO3, that's going to be that same count, 24 electrons plus 2 for that negative charge. So we have 26 valence electrons for SO3 2 minus. And so let's actually do SO3 2 minus first. So SO3 2 minus, I take my central sulfur, connect my oxygens, give lone pairs to the oxygens. And then that's 24 electrons. So for SO3 2-, I have 2 extra electrons that I can put onto the sulfur atom. The leftover electrons go onto the central atom. And so now, before I even think about multiple bonds, in fact, I don't even really need to, because sulfur is satisfying the octet rule here. It does have a positive formal charge, so it should be 6 for neutral. It only has 5, 1, 2, 3, 4, 5 electrons closest to sulfur. So sulfur's formal charge is plus, all the oxygens are negative. But in this case, I don't want to get too bogged down by thinking, do I make a double bond here? Because if I make a double bond or not, because remember how maybe we can reduce the magnitudes of formal charge, expand the octet of sulfur, or we could just satisfy the octet rule. Either one of the structures gives us 3 total bonding domains. So we get 3 total bonding domains about our central atom, no matter which structure we choose. And if I just leave them single as well, I don't then have to think about resonance, making all those bonds somehow still the same. So even if I want to think about making a double bond here, it's going to resonate to here, it's going to resonate to here, and then it's going to be the same bond across the whole structure, but the geometry is still going to be the same name. It's still going to be the same name that I get with 3 total bonding domains plus 1 non-bonding domain. That's 4 total. And so this should be a structure just like ammonia. So I should have a central sulfur lone pair, and then my oxygens in that geometry like this. This should be trigonal pyramidal. Now, whether or not I sketch it to get the name, I think it's helpful. But trigonal pyramidal is the name that I would assign to the molecular geometry of SO3. Now, within that geometry, what do we expect this bond angle to be? It should be 109.5 because it's tetrahedral domain, but it should be a little bit less than 109.5. How much less? Hard to know, but it'll just be, I think my best prediction for this bond angle would be some measure less than 109.5 degrees. And it's, again, because the lone pair, bond pair repulsions. Okay, now without the extra 2 electrons, SO3 has a little bit of a different geometry. SO3, just 24 total electrons, doesn't have the extra 2 electrons here, so we're just going to end up with our Lewis structure kind of starting. And I'm going to think ahead of its geometry too, because once I see it only has 3 domains all bonding, it's going to be in that trigonal planar domain. So I have a geometry that looks like this. Now, I do need to make at least 1 double bond. I have a 3+ formal charge on sulfur, and I have an octet that's not yet filled, so I at least want to make 1 bond. And if I have that Lewis structure, then my formal charge on sulfur is +2. The formal charge in the outer rows is -1, 0 with the double bond. And then from there, I have to then picture resonance. So resonance would make all of these bonds identical. It would make all of those bonds be the same. So the real structure would look like sulfur, oxygens, extra bond, where all these bonds are identical. And remember how we described those bonds as being 4/3 bonds in terms of their bond order? So not quite single, not nearly double on average, but they all average out to be the same. The key is that all 3 of those bonds are identical to each other within the model of resonance that structure would depict. Now, we could also instead have said, well, what if I use this Lewis structure here and just minimize the magnitudes of formal charge and just expand the octet of sulfur? Well, it's actually pretty good for this demo, just because that gives you another picture where SO3 has 3 identical bonds, that they're all the same. So now, when I'm thinking about the prediction of bond angles, you see how the prediction is it's perfectly 120 degrees within the double bonded structure, but also within the resonance picture. Because I have 3 identical bonds, 3 total bonding domains, all of them non-bonding. So there's no reason why 2 of the bonds should get closer together than the other 2 further away. If I look at just one of the resonance structures, if I call this resonance structure A up here, the structure of SO3 never looks like A. So I never end up with the bond angles that are single getting closer together, because there's really not 2 single bonds and a double bond within SO3. So a complicated picture for some molecules where resonance kicks in anytime we have equivalent yet different Lewis structures. Average out the structures for the real structure of the molecule, consider that, or picture a structure that shows you equivalent bonds, like in SO3 here. So all the bonds are perfectly 120 within SO3. Now let's get into this discussion of polarity of bonds, where something really interesting happens where even though some molecules have polar bonds, sometimes they end up being nonpolar molecules. And so bond polarity from chapter 8 is a measure of how equally or unequally electrons are shared across a bond. So if I look at any particular bond, like let's look at CO2 for example, I'm just kind of looking at, there's a difference of electronegativity between C and O. So oxygen should be partial negative, carbon should be partial positive, because of the electronegativity difference, and oxygen's more electronegative, so it should be pulling electrons towards itself. Now, even though oxygen is doing this, and we look at this bond here, and we said that definitely is a polar bond, meaning the atoms aren't zero charge, the atoms pick up some type of charge. We can actually have the molecule be nonpolar depending on how those bonds are situated. So, and if we just look at bonds, it's all about electron sharing, relative electronegativity differences. So we have a nonpolar bond if the electrons are shared equally, and a polar bond if one of the atoms has a greater electronegativity, greater force to pull the electrons closer towards itself. But in terms of a molecule, so when is a molecule polar? A molecule is polar when it contains polar bonds, but then also the bonds are situated in a way that the molecule can become what we call polarized. And then a molecule becomes polarized when its ends have different charges. So when CO2 has the exact same charges on both of its ends, it doesn't end up having one of these things that we call a permanent dipole moment, or it doesn't have something that we would call it to be a polar molecule. One thought would be for CO2, we'll see this on the next slide too. Imagine I put a positive charge here. Which end of the molecule is going to fight for that charge and flow towards it? Do you see how both of the oxygens are going to fight over it and just end up spinning and getting into like an argument over which one wins? And so neither one's going to end up allowing the molecule to drift towards that positive charge. We need there to be a net pole or a net end of the molecule that has a different charge in the other end, so that that end of the molecule, the negative side, can head towards the positive charge. So let's take a look at this slide here. So CO2 ends up being perfectly nonpolar, and it's really important for CO2 to have its properties that it has based on it being nonpolar, where even though it has big differences of electronegativity and oxygen picks up a big negative charge, again, if I dangle that positive charge, these ends, the negative ends of the molecule, just fight with each other and can't really flow towards that positive charge. Now imagine how water is a little bit different. Water has, because it has a bent bond, now due to the bent bond, I have a different charge on this side of the molecule. I have a net negative charge up here, oxygen's more electronegative. Our hydrogens go partial positive. And so I have this positive charge developing over here, this negative charge this positive charge here. And so this end of the molecule is negative, this end of the molecule is positive. So now when I dangle a positive charge, the negative end of the molecule can head towards that positive charge and flow towards it. The fact that water has a dipole moment is going to give two water molecules a stronger built-in attractive force with each other than two CO2 molecules. And it's really hard to picture why that would be the case, because CO2 does have some charge developed in it. So we do have charge being developed in CO2, but if you put two CO2s adjacent to each other, it's just almost like negative repulsion. There's no built-in way for two adjacent CO2 molecules to sense any greater attractive force. Now, it's really important, if water turned out to be linear, if that bond in water for whatever reason were linear, it would have had that dipole cancel out as well, and it wouldn't have been a polar molecule, which would have greatly weakened its intermolecular force for itself. So in other words, water would never have been a liquid at room temperature on Earth if it were nonpolar. It's really important for water to have its properties, given that it has this permanent dipole built into its structure. And if CO2 somehow had the dipole, then we'd have liquid CO2 probably on the surface of Earth. Instead, CO2 is a gas at room temperature. CO2 actually sublimes at minus 78 degrees C, straight from solid to gas. It never really hits the liquid phase. That's a topic for later. But CO2 is well into the gas phase at room temperature due to having a weaker intermolecular force of attraction with itself. Well, guess what we can do now? We can go back and predict for a bunch of molecules that we've looked at whether or not they are polar versus nonpolar molecules. But one of the things that's kind of interesting is if you think of CO2, BF3, CH4, CF4, any molecule that's going to fit into perfect linear, perfect trigonal planar, perfect tetrahedral, perfect trigonal bipyramidal like PCl5, PF5, perfect SF6, anytime those bond angles are exactly what you expect for the base geometry and all the atoms are exactly the same on the central atom, the dipole moment will disappear and will go to zero. Okay, so let's give a couple predictions here. We just did the structure for SO3 earlier. So if I'm picturing the base structure of SO3 like this with the double bonds or just with these equivalent bonds here, this would be trigonal planar electron domain geometry. Maybe trigonal planar molecular geometry as well. The bond angle should be perfectly 120 degrees. And then do you think that should be a polar or non-polar molecule? What do you guys think? Well, let's picture this geometry here real quick, where the formal charges are all 0 for oxygen. Do you think oxygen really is 0 charged in this structure? Probably not, because it's the more electronegative atom. It's going to pull the electrons closer towards itself and pick up a partial negative charge. But now, does one end of that molecule have a different partial negative charge than some other end of the molecule? No, all the oxygens share in the exact same charge as each other. All the ends of this molecule have the same charge, so this should be a non-polar molecule, just like CO2. So anytime we have perfect bond angles and the same atom, we don't try to get too complicated. We'll show you a couple examples as we go. I guess it maybe are a little bit more complicated. But if I change one of the O's to some other atom, that would change the whole idea that the atoms have the exact same charge. But there's really no common example where we have like SO2 with some other atom instead of the O there. Now, what if we get rid of one of the O's? What if we go to SO2? SO2 has 6 plus 2 times 6. It has 18 total electrons. So it has a central sulfur, 2 oxygens, lone pairs around the oxygens. That's 16 of the electrons, just making sure we see how we get the extra electron pair onto sulfur. Now we should make at least one double bond. If we do, we can then pick up the resonance over to here, or we can just go ahead and make 2 double bonds if we want to zero out the charge and expand the octet of sulfur. But the key would be I have 3 total domains. So I have 1, 2, 3 total domains. So that's still going to be trigonal planar electron domain, but this takes on the name, what we call the molecular geometry name here. What do you guys think? Should be bent. Anytime I have 3 atoms, it's either bent or linear. This clearly isn't linear. This bond angle here should be closer to 120. And I can even predict it's a little less than 120. Even if it were perfectly 120, you can see here that the oxygens have a negative charge. So it's either -1 and 0 balancing out in the true structure. So if I'm picturing resonance effect, the resonance effect is going to make each oxygen have exactly the same charge, but it doesn't matter. I still have a positive charge up here and a negative charge down here, and so I still have a negative end and a positive end. So SO2 ends up being a polar molecule. So we get a polar molecule for SO2. So I need there to be some lone pairs in the structure to kick me into being polar, and then I need the bonds to be arranged in such a way I can get there. OF2 has 2 lone pairs. We've done the Lewis structure a few times, but if you forget, just sketch the Lewis structure. You get 2 lone pairs, 2 bonds to fluorine. We end up with a bent bond as well, and this has to be polar. So we'll look at a bunch more examples of polarity. Let's wrap up with the quiz for it was. So we'll wrap up with our quiz today. Keywords: curry. And that'll do us for today. Enjoy the slight bit of winter weather we get today. And by Wednesday, I think we're back to normal. So today.